Einstein's special theory of relativity, published in 1905, is one of the most mind-bending ideas in physics, but it can be understood without advanced math. It fundamentally changed how we think about space, time, speed, and reality itself. I'll explain it step by step in plain language, using everyday analogies and thought experiments. The two core ideas, postulates. Einstein built the theory on two simple but revolutionary principles. 1. The laws of physics are the same for everyone moving at a constant speed. There's no absolute rest or special frame of reference. If you're in a smooth-moving train, spaceship, or lab, and you do experiments, drop a ball, bounce light off mirrors, etc., the results will be identical to someone standing still on the ground. Motion is relative. No one can claim they're truly stationary while others are moving. 2. The speed of light is always the same, about 300,000 kilometers per second, 186,000 miles per second, no matter how fast you're moving or how fast the light source is moving. This is the weird part. In everyday life, speeds add up. If you're on a train going 100 kilometers per hour and throw a ball forward at 20 kilometers per hour, someone on the ground sees the ball going 120 kilometers per hour. But light doesn't work that way. If you shine a flashlight forward on that train, the light still travels at exactly 300,000 kilometers per hour relative to both you and the person on the ground. It never adds or subtracts your speed. These two rules seem innocent, but they force reality to bend in strange ways to stay consistent. What happens as a result? To keep the speed of light constant for everyone, space and time have to stretch and shrink depending on relative motion. Here are the main consequences. 1. Time dilation. Time slows down for moving objects. Time isn't universal. It depends on your speed. A clock moving fast relative to you will tick slower from your perspective. Thought experiment. The light clock. Imagine a simple clock made of two mirrors with a pulse of light bouncing up and down between them. Each bounce is one tick. If the clock is stationary relative to you, the light travels straight up and down, a short path. But if the clock is moving sideways fast, say, on a spaceship, from your viewpoint, the light has to travel a longer diagonal path to catch the moving mirror. That longer path means it takes more time per bounce, so the clock ticks slower. The moving person sees their own clock as normal, but they see your clock running slow. It's mutual and relative. Real-world example. This has been tested. Particles called muons created high in Earth's atmosphere by cosmic rays should decay in microseconds and never reach the ground. But because they're moving near light speed, time slows for them, from our view, and many more survive the journey. 2. Length contraction. Moving objects get shorter. Objects shrink in the direction they're moving, but only from the perspective of a stationary observer. The faster they go, the more they contract. Width and height stay the same. This helps keep the speed of light consistent. It's like space itself compresses to make room for the weird rules. 3. Relativity of simultaneity. Events that happen at the same time for one person might not be simultaneous for someone moving relative to them. Classic thought experiment. Train and lightning. Imagine you're standing midway on a platform as a fast train zooms by. Lightning strikes both ends of the train at the same moment. From your view, since you're equidistant, you see the flashes simultaneously. But to someone in the middle of the train, the front flash arrives first because the train is moving toward it and away from the rear one. So for them, the strikes aren't simultaneous. Now is relative. There's no universal present moment across space. 4. Mass energy. Equivalence. E equals mc squared. E equals sign mc2. The most famous part, energy E and mass m, are two sides of the same coin linked by the speed of light squared, c2. A tiny bit of mass can convert into a huge amount of energy because c2 is enormous. This explains nuclear power and bombs. Splitting or fusing atoms releases energy from converted mass. Common paradoxes that aren't really paradoxes. The twin paradox. One twin stays on Earth, the other rockets to a star near light speed and returns. The traveling twin ages less and comes back younger. It seems paradoxical. Who's moving? But it's resolved because the traveling twin accelerated, turned around, breaking the symmetry of constant motion. Special relativity only applies to constant speeds, no acceleration, that's general relativity. At everyday speeds, cars, planes, the effects are tiny and unnoticeable, which is why Newton's laws worked fine for centuries. Why does this matter? It underpins GPS, which corrects for time dilation, particle accelerators, nuclear energy, and our understanding of the universe. It shows space and time aren't fixed backdrops. They're flexible, intertwined into space-time. The theory is counterintuitive because we evolved at slow speeds, but experiments confirm it over and over.